So, this is going to be a video on the Chapter 2 study guide for stats, on statistical displays and graphs and whatnot. So the first one here asks us to describe the advantages to the following statistical displays. Because again, we went through a few of them, so these are the three common ones here. So what are the advantages to using a stem plot? And again, usually it's good to think of at least two. So one thing that's good for stem plots is that allows you to see all the data. So you can actually see all the individual data points. You don't kind of categorize them into categories. You can see exactly what the data points are without having any estimation or, again, categorization going on. It also allows you to organize the data in an easy to read way. So instead of having all the numbers splayed out, in random order, a stem plot actually orders them, organizes them, and makes it easier to read. Now, again, this is kind of generic, but again, for stem plots, it's one of the benefits to it. Frequency distributions. So one good thing about frequency distributions is that it allows you to see outlier. I thought that's how you spell it. Anyway, outlier categories. So that's not how you spell categories, I know. But it allows you to see outlier. I think that's wrong. I think that is how you spell outlier. Anyway, it allows you to see outlier categories. So again, if you have one category with 100 or one category with 0, it's an outlier. And then one other thing about frequency distributions is that it allows you, or let me say this way, it shows the shape of the distribution. So you can see whether you're skewed on the high end, you're skewed on the low end, or if you have most of your stuff around the middle. A frequency distribution allows you to see where the bulk of your data is. So again, it kind of shows you the shape, which is also true for histograms as well. You could say for histograms that it also shows the shape of the distribution. Because histograms and frequency distributions are kind of going hand in hand. They're kind of related. But the main thing about histograms, it allows you to visually see the difference between the categories, right? So again, those bars there, categories, those bars there really do let you see how far apart or how much more one category is than another, rather than just look at the number, right? So 20 and 10, okay, you can see that 20 is 10 more than 10, but if you see it on a bar, then that kind of gives the point a little bit more weight to it, and it's easier to comprehend in that case. And there are a few other pluses and minuses between the distribution here, so these are not the only answers you can come up with. These are just the answers that were off the top of my head here for these categories. So again, if you can think of two advantages for each, then you're set. And again, these are not the only two, right? What is the difference between a histogram and a Pareto chart? So basically, the main difference, the only difference, is that a Pareto chart is organized from largest category to smallest, right? It's organized from largest category to smallest from left. Let me go down here. From left to right. Left equaling most / largest category. So a Pareto chart, a histogram might look like this. So maybe this would be a histogram, right? So this could be one histogram that you might encounter, right? So you have something like this, a big bar there, small bar there, middle bar there. So that's a histogram. A Pareto chart always looks like this. Always kind of looks like a stepping stone. Now it doesn't have to be equal steps down, but the largest one is always on the left, right? It's always biggest, next biggest, next biggest, next biggest, or least, right? So a Pareto chart is organized largest to smallest. A histogram can be, any which way. All right, using the frequency table to answer the next 4 questions. There you go. We'll do there. What are the class boundaries for the 301 to 400 interval? All right, so the class boundaries, remember, are the invisible walls that are kind of separating your categories. So here we have 200 to 300, 301 to 400, 401 to 500. So what's the wall between 300 and 301? Well, it's 300 400.5. Right? That's the class boundary right there. That's the wall that we have to go from 300. We have to go from 300 to 300.5 to 301. Right? So this is the boundary. This is what we would use in a histogram if you're making this into a histogram. Right? That's the invisible wall between the first and the second category. And then between the second and the first is 405 or 400.5. Right? Because again, that's the wall between 400 and 401 is that little 0.5 in the middle. So these are the class boundaries. These are the walls that kind of separate the second category from the other two. What is the class width? So the class width is how much you're going from each one down below. And by the way, I think I made a correction on the study guide. This should be 201, not 200, because remember the class width has to be equal. So in this case, it's always a 100 jump, either going from the top end, or if you're going from the low end, that's still 100, 100, 100. So the class width here is 100. Right? There's a 100 unit jump between the first and the second, second and third, third and fourth, so on. Create a relative frequency table that corresponds to the original. So a relative frequency table means your categories are the same. So we have 201 to 300. We have 301 to 400. We have 401 to 500. And we have 501 to 600. So our categories are the same. But instead of doing the numbers, we're going to do the percentage. So first off, let's add all these up together here. So if we add up 69 plus 73 plus 81 plus 65, we get 288. So in a relative frequency distribution, we do the percentages of each category, not the number of values. So this would be 69 divided by 288. This would be 73 divided by 288. This would be 81 divided by 288. And this would be 65 divided by 288. And then we make them into percentage. Don't leave them as fractions. Actually do the percentage. So 69 divided by 288 will give us 0.24, we'll say. So this is 0.24 or 24%. Here we have 73 divided by 288. We get 0.25. So this is about 25%, roughly. 25%. Here we have 81 divided by 288. We get 28%. So about 28%. And then lastly, we have 65 divided by 288. And we get about the 5 rounds the 2 up, so we'll make it 23%. So 23% as our last frequency category. Relative. So when you hear the word relative, think percent, right? In stats, when you hear the word relative, think percent. So in terms of percentages, this is how each category looks. So instead of getting the actual number of datas in each category, we're getting the percentage of datas in each category. And if you add up all the percentages, they should come out to be close to 100. They're not going to come out to be exactly 100 in most cases because we are rounding here. But if we add up all these here, oh, actually we get exactly 100, so great for us. Our rounding in this case worked out. But if you get like 101 or 99 or 100.25, something like that, that's fine, right? Again, it should just be around 100, not exactly, because you're probably going to be rounding your percentages. Now, a cumulative frequency. A cumulative frequency changes both the categories and the values you're writing down. So remember, a cumulative frequency is that each category is itself and everything below it. It kind of rolls around. It's kind of like rollover minutes or something like that. So the first category is, we're going to say 300 or less. Now, actually, the first category you can write the same as well. So if you wrote this as 201 to 300, that's also okay because the first category is kind of special. But the amount in the first category is still 69. That's fine. But my next category isn't going to be 301 to 400. It's going to be 400 or less because this is including everything from its category and below. So this is actually 73 and 69 together. 69 for the first category plus 73 for the second category gives me 69 plus 73. Whoops. 73. We get 142. So again, cumulative means itself and everything below. So this is not going to be 401 to 500. This is going to be 500 or less. So it's going to be everything from the first two, 142, plus itself, 81, which is going to give you 223, if I remember correctly. Yeah. And then this next one's going to be 600 or less, which is going to be 223 plus 65, which is going to give me 288, which is basically your last category should be basically your total. Should be everything together. Right? So remember, cumulative changes both the category listings and the amounts you're writing out, whereas relative frequency simply changes the amounts in that column. These categories here don't change with relative frequency. All right, so reading a diagram here, reading a relatives, again, this is relatives, this is all percentage based. This is 40%, not 0.4. What percent of people were between 65.95 and 71.95? Well, that's pretty easy. Here's 65.95, here's 71.95. We're simply going to add everything between them. So 0.4 for the first bar, 0.17 for the second, 0.12 for the next, and we just add them up. 0.4 plus 0.17, 0.17 plus 0.12, we get 69%. So 69%. Right? So again, you just add up everything within the boundaries there. Now this one's a little tricky. How tall could the tallest person have been measured in inches? Well, you look here and say, oh, well, that's going to be 75.95, right? That's how tall the tallest person could be. That's the last category. That's the maximum amount in the last category. Not quite. Remember, with histograms, these are not the categories. These are the boundaries. These are the boundaries between the categories. So this right here is not 73.95 to 75.95. This is actually 74 to 75.95. So notice here, each one ends in a 95, 95, 95, 95, 95. That means that the boundaries here are 0.05. So this is 0.05 units less than the lower limit of this class. This is 0.05 units more than the upper limit in this class. So this class upper limit, this is not 61.95. This ends at 61.9. Then we write 61.95 as the invisible wall. And then this category right here represents everything from 62 up to 63.9. And this is 64 up to 65.9. And 66 up to 67.9, and so on. So the tallest person is not 75.95. The tallest person could be 75.9. Right? Again, you have to take off the little boundary here to actually get the value. Okay? So 75.9 is the tallest person, not 75.95. Right? Again, you have to take off that individual boundary there before you jump to your answer. Now, again, this is just a possibility. It doesn't mean that somebody is actually 75.9 inches. This is just the highest possible person that they could have measured, the tallest possible person they could measure. What percent of people were between these two values? Okay, so once again, 65.95, 67.95. What percent of people were between those values? Well, right here, 40%. So 0.4, 40. This is the exact same thing as the first question, except there's only one category, so there's nothing to add. You just, tie them up and you're good. Okay? All right, so again, the key word there that it was relative frequency, not just frequency. Make a stem and leaf plot of the following data. Okay, so we're going to have the first two numbers in this category and the last number in this category. There's a few ways you could make this, by the way. In general, I'm going to do it this way, though. So let's see, my smallest two numbers in the front are 11. So I'm going to do 11, 12, 13, 14. So from 11, I'm going to have 119 and 115. So I think 115 is the smallest one. So we're going to have 5, 9. I think that's it for the double ones there. All right, so now for the 1-2s. So 127, 121. 121 looks like the smallest. So 121. 127 would be the next smallest. 128 would be the next smallest. And then 129 would be the next one. That takes care of all my 1-2s. Now for the 1-3s. So 131, 133, 135, and 139. Whoops, there's two 133s. I almost missed that. So you do have to count the double ones. Remember, a stem and leaf plot shows all the data points, even the repeats. So two 133s, and then a 5, and then a 9. and there's only one 1, 4. And then over here I'd have my key. So my key is that we'll say 1, 1, 5 corresponds with 1, 1, 5, 115. Now again, you could make this where you put the ones here and then you have like 1, 2, 1, 3, 1, 4, but that'd be kind of silly because your front numbers would just be all ones, right? So I had to split up like this. Otherwise, if I just use the front number, I'd only have one category, which again wouldn't make this any better. So. And again, you should be able to do this backwards for your quiz as well. So I should be able to give you this data and ask you to give me, say, the largest data point, and you know that, oh, that's 114 or 145. Or I could say, here's a stem and leaf plot. Give me what the original data set is. And again, you should be able to go from here to here, as well as from here to here. Again, you should be able to go both ways. So pie charts. Pie charts are really good at percentages. So we have 9,225 vehicles surveyed. Um, how many hatchbacks are there? So 31% of these were hatchbacks. So 31% as a decimal, going from last chapter, is 0.31. And you times that by the total number of vehicles surveyed, 9,225. And so, come on, 0.31 times 9,225 gives you 2859.75. 2859.75, which we round up to 2860, because again, the 7 rounds the 9 up, which rounds the 5 up. Right, so, boom, right there. And then this is just the backwards version. So what percent of animals in the shelter are dogs? Well, first we have to figure out how many animals total are there. So 1 plus 3 plus 22 plus 17 plus 28. So 1 plus 3 plus 22 plus 17 plus 28. We get 71. So what percent are dogs? Well, 28 divided by 71 gives me 28 divided by 71. 39%. So 0.394. So that's roughly 39%. Or 39.4% if you want. So again, pie chart's pretty simple if you know your percentages. So the amount of individual cursors placed on a stats teacher make a dot plot. So a dot plot is simply a number line. And then dots above the numbers representing how many of them there are. So we go from 0 to 9 here. So 0, 1, 2, 3, 4, 5. I know I sound like the Count Chocula here, but 8, 9. And so we have 1, 0. So we put one mark above 0. Dot, X, smiley face, whatever you want. We have 1, 1. So we'll put another X above 1. We do have 1, 2. So 1, 2. We have no 3s, but we do have a 4. We do have a 5. We have 2 6s, lucky us. 2 7s, lucky us. No 8s and 2 9s. Once again, lucky us. So there's your dot plot. Again, dot plot is a very simple way of organizing data. It really doesn't actually organize it per se, but it's almost like a easy-ish histogram almost. Kind of like a lazy histogram, I guess, even though it probably takes more work to do a dot plot because you have to do every single data point. But again, it's kind of a lazy man's quick histogram. And then finally, a Pareto chart. Remember, a Pareto chart has to go from biggest to smallest, like we said at the very beginning here, right? So, which category has the biggest relative frequency? That'd be walking. So walking is going to be my first category. And then I'm going to have, after walking comes car. And then after car comes bus. Ideally, these should be equally spaced bars, but I'm doing this by hand or by mouse. Then dragon. And then lastly, oh, sorry, my bad. That was plane, not walking. That's kind of confused me there. So plane was the 30 category. Walking would be the last one. Okay, my bad. So we start at 6 and we go all the way up to 30. So if we count by 5s, I think we should be good. So here's 5, 10, 15, 20, 25, 30. I just probably this is 10. So plane is 30, so boom, boom. Now, a Pareto chart is a version of a histogram, so the bars should be close together. There should be no space between the bars. So 25 for car. Bus is 22, so that'd be kind of like right here. Um, Dragon is 17, so that'd be kind of like right here. And then walking was 6, so that'd be kind of like right there. So there is my Pareto chart, right? Again, biggest to smallest in order, left to right, no space between the bars. Okay? I recommend you set up your categories first, like I did here, and then do your bars. That way you're not accidentally switching your order. If you come into it with the idea of, okay, biggest, next biggest, next biggest, if you set that up first, then the rest of it is just making a quick little bar chart. And then lastly, we have a stat plot. I know I said lastly before, but actual lastly here we have stat plot. So which stat plot best corresponds or does correspond with the data set here? Well, that can take some time to do. You don't want to check each and every point. So what you want to do is look for special points. And the special points here are these two, because you notice these are the only points with negative numbers. So if I can find out which graph got those right, that's probably the graph I want to go with. So which graph got those points right? So this point right here, I'm going to write them in more typical format. This is 0.14 comma negative 0.37. And this right here is negative 0.02 comma 0.72. So this point right here, if you remember your quadrants, right? This has a positive x and a negative y. So this point should be somewhere down here. So we should have 1 point in quadrant 4. So there's just 1 point here. And then this has a negative x and a positive y. So negative x, positive y. So we should have 1 point in the second quadrant. So positive x, negative y, that should be 1 point down here. Negative x, positive y should be 1 point up here. So which graph has 1 point in the lower bottom and 1 point in the upper left? Or sorry, lower bottom. What graph has 1 point in the lower right and 1 point in the upper left? Well, this one has 1 point in the upper left, but nothing quite in the lower right. That might be it. It might come back. So this might be a maybe here. This one definitely doesn't work because it has a bunch of points over here in the upper left. So that one's certainly not going to be it. This one, again, is a bunch of points. So these two are out. I should only have 1 point down here because I only have 1 point that has a negative x and a positive x and a negative y. So there's only be 1 point. So those two definitely aren't the case. So now I'm stuck between these two. So let's see here. This has here and here, and this has here and here. So these are both candidates. Let's look at these a little bit more closely here. This point right here should be negative 0.02 and 0.72. Or sorry, this is my other point. My bad. So this should be this point. So this should be 0.14 and negative 0.37. So 0.14. So here's 1. So 0.14 and negative 0.37. That looks like it's pretty good there. Well, hold on. This is way far out for 0.14, right? 0.14 should be pretty darn close to 0. This is halfway to 1 almost. So this one probably can't work because this point is not at 0.14. It's probably at 0.5 something. Again, it's almost halfway to 1. So this is the best option we have. Part C here, number C. This is our answer here. And again, you can kind of see this with the other one too. Negative 0.2, right? Negative 0.02. That's going to be pretty darn close to 0. And this is a little far out there. And also 0.72. That's going to be a y-coordinate that's pretty close to 1. Well, this y-coordinate is nowhere near 1, whereas this y-coordinate is pretty darn close to 1. So again, this also fits the second point as well. So once you've narrowed it down, kind of look at your graph, fine-tune a little bit, and see which points match your two unique points. Now, again, you could just kind of pick points randomly and just sort of check to see which graph fits them. But again, this will save you some time if you can focus on the points that are oddballs and see which graph got the oddball ones right. And then once you narrowed it down, look for particulars to make sure that you actually get the right one. All right, so that's it for this video. Again, hopefully it helped you out. If it didn't, let me know. I'll be glad to answer any further questions, comments, or concerns you have. Otherwise, have a good day.